Hello everyone, welcome back. In this video, I'll be covering section 3.9, which are related rates. So far we have seen the derivative rules, sum, difference, quotient, product, power rule, and all that. And then we saw implicit differentiation, logarithmic differentiation, when we saw some applications of derivatives, then interpretation of derivatives as rate of change, and then how it is applied to physics and engineering problems. And we saw some applications to related growth and decay problems. And now we are seeing them in related rates. So let's related rates, the word itself suggests that it's a relation between two variables. And if we know the rate of change of one, and we can determine the rate of change of the other, provided they are connected by a relation. So let's take, if we are pumping air into a balloon, both the volume and the radius of the balloon are increasing, and their rates of increase are related to each other. But it is much easier to measure directly the rate of increase of the volume, because it's bigger, than the rate of increase of the radius. If a related rates problem, in the related rates problem, the idea is to compute the rate of change of one quantity in terms of the rate of change of another quantity, which may be more easily measured. The procedure is to find an equation that relates the two quantities and then use the chain rule and differentiate both sides with respect to time. So let's take a problem and see, and then we can generalize the method. The air is being pumped into a spherical balloon. The shape is balloon and spherical, so that its volume increases at a rate of 100 centimeter cube per second. How fast is the radius of the balloon increasing when the diameter is 50 centimeter? So the shape is spherical. So we are looking at a spherical figure, and we are given its volume increases at the rate of. So if I denote V for the volume, this means the rate of increases at a rate of, which means dV by dt, derivative with respect to time. So anytime the word rate is used, it's it is the volume per second in this case. So it is a rate. So it denotes the derivative. In terms of math expression, it is dV by dt. How fast is the radius of the balloon increasing? It's not asking the radius, but it is asking how fast is the radius of the balloon increasing. What it is asking is dr by dt, provided r is the radius, when the diameter is 50 centimeter. What is the diameter in a sphere? Twice the radius, correct? So it is 2 times the radius. So 2r equal to 50 centimeter. So let's start off with the volume of a sphere. Which is 4 by 3 pi r cube. Okay, we'll denote that volume by the variable V. V equal to 4 by 3 pi r cube. Then as we are given dV by dt, which is 100 centimeter, what are all given here? Let's write down what is given here. Given is dV by dt, which is equal to 100 centimeter cube per second. What else is given? Diameter is 2r, which is equal to 50 centimeter. But the question is, what is dr by dt when the diameter is to r. So we cannot substitute the diameter or radius equal to 25 centimeter, half of the radius in the beginning. We have to substitute that at the end when we compute dr by dt. All right. Now let's find out the derivative on both sides. Let's take the derivative on both sides. So which will be, in this case, it is v, in this case, 4 by 3 pi r cube on the right hand side. So dv by dt equal to 4 by 3 can be taken out of the derivative. Then pi can also be taken out of the derivative. Derivative of r cube. So it is derivative with respect to r and then with respect to t. So it is 3r square outer derivative times dr by dt. So here what rule do we use? We use the chain rule. So d by dt of r cube is d by dr of r cube times dr by dt. So this part is the outer derivative and this part is the inner derivative. Which is a chain rule. So it is 4 pi r square times dr by dt. Do we know any value here? Yes, of course we know dv by dt, which is given in the problem. dv by dt is given to be 100 centimeter cube per second. So substitute that 100 for the left-hand side. At this point, you can substitute the specific, substitute. So we have 2r equal to 50. So twice the radius, r equal to 25 centimeters. So everything is in centimeters. So we will, so you don't have to convert this. So it is 4 by 25 square times dr by dt. So what is dr by dt? If you isolate that, you have to divide 100 by 4 pi times 25 square. Or it is 100 divided by 4 pi 25 times 25. So 100, 4 times 25 is 100. So it becomes 1 over 25 pi centimeter. R is measured in centimeter. Time is measured in second. So it is centimeter per second. So 1 over 25 pi. You can leave the answer like this. And if you use your calculator for this, so if you use your calculator, I see that 1 over 25 pi turns out to be 0.0127 centimeter per second. That's what you have to enter in the problem as the answer. So dr by dt, when r equal to 25 centimeter is given by our rate of change of radius. So how fast is the radius of the balloon increasing? So the radius of the balloon is increasing at the rate of radius of the balloon is increasing at the rate of 0.0127 centimeter per second. All right. So so notice in this problem, the guidelines for doing these problems is that first you understand the problem. So understand the problem, then understand the problem, just like any other word problem. And then and then underline the key information given in the problem. Information given in the problem. What is given in the problem? What is given? What is asked? Okay. If a diagram helps, use the diagram. And write the rates given in the problem. And set up an equation. Equation connecting the variables. Equation connecting the variables. Equations connecting the variables. What is the other thing that you would do? Take the derivative. Take the derivative. The last part, substitute the specific. In this case, so if you don't substitute this information in the beginning of the problem. So after you take the derivative, only you need to substitute the specific. So these are some of the things that you can remember, the steps. So we normally use a mnemonic for this called DRED. Yes. D for the diagram, if necessary, if needed, okay, if it helps, a chart, and R is the rates given in the problem, and set up an equation, take the derivative, and substitute the specific. Let's try problem number 2 here. There are some additional problems given. Some of them have been done already in a video. For the practice exam videos or the chapter videos, you can check. Those are 21 and 29. These two problems are already done. Then in this video, I'll do some of the problems, homework questions here, along with maybe practice exam 13. Okay, PT 13 in this video. So let's do number 2. If A is the area of a circle with radius r and the circle expands as the time passes, find dA by dt in terms of dr by dt. B, suppose oil spills form a ruptured tank from a ruptured tanker. Oil spills from a ruptured tanker and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second, how fast is the area of the spill increasing when the radius is 30 meters? The idea is kind of similar to the one that we have done. To make more room, I have copied it over here. So let's do problem number 2. A is the area of the circle. Now we are talking of a circle area. Area A is denoted by pi times r square, which we know. R is the radius, and the circle expands as time passes. So A increases with respect to time. Find dA by dt in terms of dr by dt. So let's take this relation connecting the variable A and R. Then what is dA by dt? Which is dA by dr times dr by dt, which is chain rule. The reason that in this case, the difference between the earlier one and this one, the earlier differentiation and this one, is that we are actually here, we will be considering A as only as a function of R usually. But when it comes to related rate problems, we have to remember that both A and R change with respect to time. So they become a function of R. So that's why we have dA by dt equal to dA by dr times dr by dt, outer derivative times inner derivative. What is A if you differentiate this with respect to R? So it is pi is a constant, derivative of R square is 2R. So that will be 2 pi R, which is outer derivative. And then dr by dt, just keep it as dr by dt. So this part is 2 pi R, and we are keeping dr by dt as is. Now, that answers the first part of the question. So dA by dt, the right dA by dt in terms of dr by dt, which is the first part. The second part, suppose the oil spills from the tank and spreads in a circular pattern. If the radius of the oil spill increases at a constant rate of 1 meter per second. So when you read this part, if the radius of the oil spill increases at a constant rate of, so that means the rate means the derivative. The derivative of what? Derivative of the radius. So it is saying that dr by dt equal to 1 meter per second. 1 meter per second. How fast is the area? So how fast is the area? So what it's asking is that what is dA by dt increasing when the radius is 30 meters. So everything is in meters. So 30 meters. So this is the specific. So when the radius is 30 meters, so the last part is something specific. So we are calculating the derivative only when r equal to 30. So it keeps on changing. The area keeps on changing, but we want the rate of change taken when the radius becomes 30. So this is the last part, substituting the specific. So let's take this relation and substitute whatever we know. So how fast is the radius? So we have to find out dA by dt. Then you are given 2 pi. Radius is 30 meters. And dr by dt is given to be 1 meter per second. Then we want to find out dA by dt when r is 30 meters. Right? So in other words, dA by dt at r equal to 30 meters. So we substitute r equal to 30. dr by dt can be replaced by 1 meters per second. So it will be 60 pi. A is meter square divided by seconds. So it is 60 pi. So let's try number 5. A cylindrical tank with radius 5 is being filled with water at a rate of 3 meter cube per minute. How fast is the height of the water increasing? So we are talking of a cylindrical tank. It is cylindrical tank. The radius is 5 meters. The radius does not change. The throughout cylinder, the radius will be the constant. So what is the cylinder shape? The cylinder shape would be something like this. The radius is not varying. It is r equal to 5 meters. It's filled with water, and it is being filled with water at a rate of 3 meter cube per minute. So here, if you look at the actual problem, a cylindrical tank with radius 5 is being filled with water at a rate of 30 meter cube per minute. So that means because of, you see that meter cube there, they're telling us that the volume is what the cube. If it is in square, it would be talking about the area. If it is cube, it means it's talking about the volume. So what is given here, because it is per minute, so what is given in the problem is rate of change of the volume, that is equal to 3 meter cube per minute. How fast is the height of water is increasing? Height, that means dH by dt. You're asking dH by dt. So what being asked? What is asked? dH by dt. Here, as a radius is always a constant, so we can assume that it is, the specific is radius equal to 5 meters, right? So we want to find out dH by dt when r equal to 5. So first we need the formula for the volume of the cylinder. So volume equal to pi r square h. So radius, the base area times height, pi r square times h. In this case, radius is a constant, so we can substitute that 5 there, so which will be 25 pi h, that is the volume. Now you take the derivative. Take derivative on both sides. So with respect to time t, so dv by dt equal to d by dt of 25 pi h. So it is 25 pi times dh by dt. So what is dv by dt given in the problem? 3. So we are solving for dh by dt. So isolate dh by dt on one side, divide 3 by 25 pi. So that will be in terms of, because h is measured in meter, t is measured in time. So we can say this is meters per minute. So the height of the cylinder is changing. Height is increasing at the rate of 3 meter, 3 over 25 pi meter per minute. Meters per minute. Okay. Next, let's try the problem, practice test number 13, given in the additional suggested problems. This is the one in this video, in the concept video. A plane flying horizontally at an altitude of 1 mile and a speed of 500 miles per hour. So altitude of 1 mile and the speed of 500 miles per hour passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing when the plane is 2 miles away from the station. So first we have to understand the problem. So a plane is flying at an altitude of 1 mile at a speed of 500 miles per hour. So this is telling us some rate, right? The speed, because it says miles per hour, it means it is the rate, the horizontal rate, because it's flying horizontally. So it is the horizontal rate, okay, horizontal rate. It passes directly over a radar station. Find the rate at which the distance from the plane to the station is increasing. Again, we are asked to find out the derivative of a distance. When the plane is 2 miles, this is specific. So substituting the specific comes after you do the derivative and all that. So is there any diagram that helps us for this problem? I think it does. So let's take, because the plane is flying at an altitude of 1 miles and it is flying horizontally. So the plane is going this way. It's going this way. And let's assume that the horizontal distance at any time is x. And then let's say it reaches this point when, and then the question is, what is the distance of the plane? How fast is the distance of the plane increasing the plane. This is where the plane is. This is where the plane is. It starts here and it goes here. And then this is the station. This is where the station is. Let's assume this distance equal to y. So altitude is 1 mile, the height. Then it flies horizontally. And then it reaches, so it starts here and reaches here. Then we have to find out the distance between B to the station. Yes, we call the distance as y. And we want to find out what is dy by dt when the distance of the plane from the station, which is when y equal to 2 miles. This is what asked in the problem. What is given in the problem? Dx by dt is given in the problem, which is 500 miles per hour. This is given. So we know that we will take the horizontal distance as x, and t is measured in hours, let's assume, because it's all given in terms of hour. So let's assume if we let t be the time in hours, and x be the horizontal distance, x be the horizontal distance traveled by the plane in miles. Okay, so we are also given dx by dt equal to 500 miles per hour. Okay. Now, by Pythagorean theorem, we can set up a relation between the variables. So, by Pythagorean theorem, so we have 1y square equal to 1 square plus x square, or x square plus 1. So we have a relation. We've set up an equation. Now let's do the derivative on both sides. Take derivative on both sides. So d by dt of y square is d by dt of the right hand side. So what do you have on the left hand side? Y square. What do you have on the right hand side? X square plus 1. So remember that both y and x vary with respect to time. So it is 2y dy by dt, which is by chain rule. It is 2x times dx by dt, chain rule again, plus derivative of 1, which is constant. So finally, what do we have to find out? Dy by dt. So let's solve for dy by dt. Dy by dt would be 2x times dx by dt over 2y dy, it's over 2y. All right, so 2 and 2 can be cancelled out. So it's x over y times dx by dt. So we know the value of y, which is equal to 2 miles. So we are substituting the specific. Substituting the specific is only at the end. So y equal to 2. But do we know x? Because in a right triangle, if we know y, if we know this one side 1, we can get x, isn't it? So y square equal to x square plus 1. So if I substitute y equal to 2, I get x square plus 1, which means x square equal to 3, or x equal to plus or minus square root of 3. But in the context of the problem, x has to be positive. It measures the horizontal distance. So x cannot be equal to negative radical 3. So x is only positive radical 3. So we will substitute all that values in this relation, x equal to positive root of 3 divided by 2, then dx by dt, which is given in the problem, which is 500. We are substituting the specifics here. Dx by dt equal to 500. So what is dy by dt? Equal to root 3 times 250, if you can cross it out. If you use your calculator, you can leave it like this. What is y? Y is measured in miles and t is measured in hour. So the distance between the plane to the station is increasing at the rate of 250 times radical 3. So if I show that in the calculator, it becomes 433.0127 in my calculator. So you have to write that as in terms of units. So here, because it is the numerator for dy by dt, numerator is measured in meters, miles, the denominator is measured in hour. So you have to say 433 miles per hour approximately. So the plane, the distance between the plane to the station, that is what the y is, the distance between the plane to the station. So the distance between the plane to the station is increasing at the rate of, why do you use the word rate? Because it is dy by dt, derivative. Right? You are using the derivative, which means rate of change. At the rate of 433 miles per hour. So in a word problem, make sure to write your answer in words and whatever is asked in the problem. And don't forget to write the appropriate units for the problem, especially in word problems. So as I said earlier, in this exercise, try as many as you can, because it is different from whatever you did before. Good practice is necessary for this problem, this exercise. And PTPF 21, practice exam, practice final, problem number 21 and 29 are done in the practice exam videos or the chapter videos. You can check them out. In this concept video, I have done these problems. Problem number 2 is done here. Then problem number 2. Then we did problem number 5, and we did problem number 13 in this video. This is called concept video. Right? See you guys for the next section, which is 310.